This is the first problem from chapter 8 on electric force and electric fields. And it says the nucleus of the helium atom contains two protons that are separated by about 3.0 times 10 to the negative 15 meters. Find the magnitude of the electrostatic force that each proton exerts on the other. And in parentheses, the protons remain together in the nucleus because the repulsive electrostatic force is balanced by an attractive force called the strong nuclear force. Okay, so here are the couple of protons. The ones in red here, and then there are a couple of neutrons. A typical helium atom contains two protons and two neutrons. It's possible for it to contain a third neutron or just one, but it always has to have two protons, and that defines it as helium. In any case, this would be the distance they're asking about between the middle of the protons. Of course, the whole thing is a model anyway. This is how we envision. Okay, I don't know how this happened here. How we envision how the nucleus looks inside. We make kind of balls or spheres and go from there. And this is, of course, the separation distance they were talking about. I'm trying to figure out my own tablet here, and it kind of tries to play tricks on me again. Boy. So here's the separation distance, d equals, let's see what that was again, 3.0 times 10 to the negative 15 meters. And they're asking for what the force is, and really the only thing we can use here is Coulombs Force, which says that the force equals the constant K times fraction bar charge 1 times charge 2 divide by, and here I have to look if they use D for distance in our book, if they use R for radius, and they usually use R for radius. And after that, it is just a matter of plugging in numbers. I think I need a lot of space here. So where it says D right here, well, that becomes my R over here. I just said D for distance, but Coulomb's law writes R for radius or distance. So plug in the numbers here, 8.99 times 10 to the 9th. And as I said, I'm trying to figure this out. Come on. And the units are really interesting for the constant. In fact, I think I'll show them in just a moment. This is not correct yet, but I'll fix it in a moment because I want to show something there. Times, well, the charge of one proton, look it up in the book. Top of my head, 1.67, right? Yep. Nope, that's the mass. Sorry about that. Where'd it go? I ought to have it memorized. Oh, 1.602, of course. I do have it memorized. 1.602 times 10 to the negative 19 coulombs. Again, I'm trying to it keeps playing tricks on me. Come on, just give me the 19 there. There we go. Coulombs times, well, the charge of the other proton, but that happens to be the same. So I'm going to shorten this here. I'm just going to make parentheses around it, and I say that's squared. Same deal. Divide by the distance squared, which is given here in this problem as 3.0 times 10 to the negative 15 meters, and that one as well squared. Okay, back to the unit for the proportionality constant K, and I actually don't have it memorized, that unit, because it is so strange, but it's easily to be figured out the force has to come out as newtons. That's why I already wrote the newtons here. And then the Coulomb squared have to divide out somehow. So that unit, that constant, incorporates Coulomb squared. And the meter squared have to divide out. So that's why the unit looks that way, so that the coulombs are gone, the meters are gone, and the only thing that remains are the newtons. And then I'm going to put my little underlining bar here, and I'm going to do newtons here, and of course that is for you to calculate how much that is going to be. Top of my head, if I look at that here, negative 19 and there's a negative 15, so if you use the law of exponents, then it's negative 4, but that needs to be squared, which is negative 8, and then with the 9 here it's 1. 9 minus 8 is 1, and so 10 to the first, so roughly in the neighborhood of like 10 newtons or so. Well, actually a little bit more, like 40 to 50 newtons perhaps, in that neighborhood, somewhere around there. I didn't do the calculation, you do the calculation. But actually appreciable. That's in the neighborhood of maybe 10 pounds or so. And between these tiny, tiny protons, and of course the reason is because these are really, really close together. Again, my thing here about 40 to 50 newtons was kind of ballpark figure. Maybe it's a little bit less, maybe it's a little bit more. You will calculate it. Okay, I just pulled this one up here on hyperphysics. It says in the parentheses, well, as the electrostatic force tries to push them apart in that neighborhood of about 10 pounds or so, well, there has to be another force that holds them together, and that's called the strong nuclear force, which has to be at least that much. So huge forces are acting inside the nucleus. And this is just a description of it. It's kind of hard to understand. You know, there's a strong nuclear force, and in the end you just have to accept that there is, because otherwise things would be flying apart, and all we would have in the universe would be hydrogen atoms, and we don't. So there must be a strong nuclear force holding together. Here they try to explain it with that, or they do explain it with that these little particles called gluons are holding the protons and neutrons together that are being exchanged, between the quarks inside the protons and neutrons. Anyway, that's just a little bit on top of what this problem was about. Okay, the next problem is, except I lost my space in my book because all of a sudden I couldn't remember the electric charge of the proton, which I have memorized for past 30 years as 1.602 times 10 to the negative 19. Anyway, new problem. It says a small spherical insulator of mass 8.00 times 10 to the negative 2 kilograms and charge plus 0.600 microcoulombs is hung by a thin wire of negligible mass. A charge of negative 0.900 microcoulombs is held 0.150 meters away from the sphere and directly to the right of it. So the wire makes an angle theta with the vertical. See the drawing. Find A, the angle theta, and B, the tension in the wire. This will become kind of involved. In fact, the problem has a double start on it. Okay, let's see what is happening here. For one thing, they want to figure out what the tension is in the wire. So what I'm going to do is, give me one moment, I'm trying to find, I think I'm going to use blue as a color. Okay, that arrow that I just put there on the very right, I just wanted to get it back on the page. So there's the tension that we're supposed to figure out. And I guess I'll label it as such. So there's the tension. But then we have to see what kind of other forces are working on here. Obviously the electrostatic force. So there's going to be Fc between these. And notice that I write these as vectors, which makes sense because they're pointing in certain directions, so that's important. So that Fc is this way here, and I wish that would be blue like I had it earlier. Oh boy. There we go. I'm going to click there, and will I get an automatic blue one this time? No, I don't. Okay. There is a third force here, and because it's hanging from a wire, it must be its own weight, so gravity pulling it down. There we go. So FW, and actually, about that T that I wrote there, I'm going to take that back. Actually, I would like to write an FT. I just noticed I do prefer to write a force as a capital F and then put indices around it. Oh, underneath, I mean. Okay, so tension, Coulomb force, and the weight. So when I add all these forces, and you could tell me what that very, very important law is that I'm using right now, respectively, because I'm recording this to myself, you cannot tell me. So obviously this is Newton's second law, where forces are added, and because everything is in equilibrium, nothing changes its motion. In fact, it's still anyway. The acceleration comes out to zero, so the net force is also zero. And that's the equation we have to solve in order to figure out what they want us to figure out. Looks easy enough, right? But we're dealing with vectors, so we have to deal with components, so x and y components, so it's actually two equations. Okay, here's the x component. And what I have in the x is the tension times cosine, and I'm going to call this alpha because if you took the previous class from me, then you may recall that I like to have the angle measured from the positive horizontal, and the reason is that that way I can always use the cosine with the horizontal and the sine always with the vertical. Okay, and then later on we'll figure out how alpha actually relates to theta, but the outcome will be just fine. We get the right result. In a vertical, we have a tension of Ft times sine alpha, and again, that's the reason why I use that. I don't know why this keeps popping up here. Somehow I still have to figure out my tablet. So times sine alpha because it's the vertical, and now the Coulomb force that acts only in the horizontal, so Fc, and then I'm going to have in the vertical the Coulomb force is 0 because it has no vertical component in this problem, and then the weight, which is 0 in the horizontal, obviously, and that equals 0 because the net force is 0. And in the vertical, it's the weight, that is m times g, times the sine of, and look at this one here, 270 degrees, right? Measured from the positive horizontal, it's 270 degrees. That's why we're getting a negative in there. And that is again is 0 because nothing is happening. And of course Fw is written as, let's see if I find some space here, Fw is written as mass times gravity, mg. Here we go. Both of these positive numbers, the negative number comes from this sine 270 degrees. Okay, they want us to figure out what the tension is. So this one here. So that's one of our variables. And they want us to figure out what the theta is, respectively. For now, I'm using the alpha. By the way, I think you can see this, that alpha equals 90 degrees plus theta, right? Because up here would be the vertical, and then this little piece in here would be theta itself, and then 90 degrees there. Okay. So actually, oh yeah, I wanted to circle that alpha. There it is. Okay, let's see where we get started. We have both variables in both equations, so we have to eliminate something here. And the easiest way to do that is to get just these parts on one side of the equation and then the other parts on the other side of the equation, and then divide, because when I divide that with only this stuff on one side, the ft will divide out. And I will divide the y by the x, and you will see in a moment why I do that. Okay, I'm not going to change the color at this point. So ft times sine alpha, that was supposed to be an I, and that equals negative fc. Notice that fc actually will be a positive number as it points to the right, but of course I brought it to the other side, so that introduces a negative. And then ft times cosine alpha equals, and the sine 270 degrees here already is a negative, so it's a negative fw. So when I get it to the other side, it actually becomes a positive fw. And as I said, now I divide both sides by each other, and that double equal sign there looks a little strange, but that's alright. And notice what happens, of course, on the left hand side. As I said, what divides out is the ft, and what is left behind is sine theta over cosine theta. Why did I do the y divided by the x? Because I saw that sine divided by cosine will give me a nice tangent. Otherwise I would have gotten a cotangent. Would be still okay, but I would have to do some more algebra. Equals negative fc over fw. And at this point I would have to plug in numbers in order to get the alpha. Of course, what I would have to do here is divide here, put a negative in front of that, and what was I going to say? Oh, take the inverse tangent of that. But instead of writing that all down, all these long numbers, I might as well do it on a graphing calculator and show you. It saves me some space here to write it down, and a lot of effort too for me to write it down with this tablet. So let's see what I get here. Okay, there's that negative. Then in parentheses, I'm going to put the 8.99. Is that really rounded 8.99, or do they do 9.00? Sorry, I'm paging. I have to actually look that up. Yeah, they keep using 8.99. Okay, to the 9th, and then times, there's that one charge, 0.6, I go back, 0.600 microcoulombs, which is -6, times 0.900, and it's also microcoulombs, also -6. Okay, notice that right here I omitted that negative, and I did so on purpose. I'm just using the magnitudes. The reason is that my Coulomb force, this one right here, is pointing to the right, and so I need to come up with a positive, and I can only do that if I use the magnitudes of these two charges. Okay, divide that by the distance between the two, and that is 0.150 meters, and that needs to be squared. Then there's that fraction bar, and in the denominator I have the mass of this one here, which I have to look up in the problem, is 0.08 kilograms. 0.0800 kilograms times the acceleration due to gravity, which is 9.8, parentheses, put another parentheses, hit an enter. I do come up with a negative, again because of this negative, and that makes sense because once I take the inverse tangent of that, it has to put me in the second quadrant where the tangent is actually negative. Let me first check that I am in degrees. I am. So I'm going to take the inverse tangent of that number. Oops, made a mistake. Try it again. I hit the wrong button. There's the answer. I hope I didn't mess up. Negative 15. Okay, it's actually putting me into the fourth quadrant. Negative 15 degrees, which means this here actually should be 105 degrees, respectively. Actually, this one here without the negative is that theta here, 15 degrees, 15.4 degrees. As I said earlier, it's 90 degrees plus the theta, and again, it put me actually into the fourth quadrant rather than into the second, so that's why you see that negative 15 there, and the other result would have been 105.4 degrees, which still makes the theta to be 15.4 degrees. So here it is. Okay, and then actually you take just one of the two equations, and let's see, what color do I have left over here, and you plug in for Ft. So you're going to do Ft equals, I'm going to use the easier one, the second one here. Again, bring that Fw to the other side, and because here it's a negative right there, it's a negative, bring it to the other side, it becomes a positive, so it's Fw respectively just m times g, and then divide by sine theta. I'm not going to hold up here with explaining the algebra, of course you should know that. Sine alpha. Oh, take that back. Now I should erase things, or should I? Because my alpha is actually 105.4 degrees and my theta is 15.4 degrees. I have to fix that, and I don't want to do the whole recording over. So let me think about this a moment. That one is actually 105.4 degrees. I put that entry there in the wrong place, and then this one here is theta equals 15.4 degrees. That's what I meant to write. And then actually here it doesn't really matter if I use the alpha of what? Let me think about this. Yes, it does matter. I have to use actually the alpha of 105 degrees because that's how I defined my vertical force Ft. And so that is going to come out to, let's see, sorry, I'm back to green here. Now that I confused myself here for a moment, I might as well finish the problem. So what was it again? 0.08 kilograms times 9.8 divided by the sine of 15.4 degrees, parentheses, enter, and the force that I come up with is three significant figures, I think is what we used. Is that 2.95 rounded? 2.95 newtons. Just let me write a 9. Geesh, that tablet. So I might as well finish the problem since I confused myself here for a moment writing down these here. the degrees. So it's going to be the tension equals 0.08 kilograms times 9.8 meters per second squared, gravity, divide by the sine of alpha, which is given as 105.4 degrees. So I have to adhere in the calculation to the alpha that I had used. Enter, and the result comes out to 0.81, what was that other decimal? 3 newtons.